Okay, I want to show you some calculations using optical rotation measurements. So optical rotation involves taking a sample, so let me put sample with an S right here, and placing it between two polarizer filters, which I hope you've seen a demonstration of. And so what you have is you have a certain frequency of light that comes through the first polarizer, and then if it goes through an asymmetric material, the plane of the polarization actually gets tilted either clockwise or counterclockwise, so that the light comes out in a different angle, okay, on the right side of the sample. Now, you can then use this filter, okay, and let me just put this filter as some slits right here, okay, because that's what these are. These are just molecular slits right there. And you can either rotate the slits clockwise, okay, or you can rotate them counterclockwise, and therefore you can detect that the light actually has been rotated, okay. So that's why this is called optical rotation, okay. Now if I put this two filters one on top of each other like this, let me visualize, or have you visualize this, okay, this way, and then I put another filter 90 degrees to another like this, okay, then you shouldn't actually see any light going through there like that. But if there's a material that's sandwiched in between the two filters like that, then if you can see something, okay, at some angle, it doesn't have to be 90 degrees, whatever angle you get, if you can see something, then we call this a plus rotation, okay. But relative to the first filter, if you have to turn the filter in this direction to see something, that's called a minus rotation. Okay, and so what you use then is a device to do this quite precisely. It's called a polarimeter. Okay, but that's just let me. Okay, so it's just a fancy device that controls the filters. The filters that are used to do this measurement, and you need that because you actually want to get the angle, whether you have to rotate one polarizer with respect to the other like this in the plus direction or the minus direction. You want to get a precise angle from this measurement. Okay, so this instrument will give you some values, and this is a symbol for optical rotation right here. Now, how much optical rotation you get actually depends on three factors. One of them is the compound, okay, and the other one, in other words, there's an intrinsic rotation that a particular asymmetric compound will give you. And remember, you're only doing this measurement on chiral, right? Chiral or asymmetric molecules. You will not observe this rotation with symmetric or achiral molecules. Okay, and remember the other thing too right there, when do you see the plus and when do you see minus? Well, for one enantiomer, you will see a plus rotation, and for the other enantiomer, you'll see a minus rotation. Okay, so this is an important property of enantiomers, and that they have a different optical rotation, which is opposite, either plus or minus. The other thing too that I want you to remember is that we used to use the symbol little d for plus and little l for minus. You can still find listing. In fact, the other day I saw a bottle in my lab that said DL and then something like that, okay, just to indicate that you had both. We call them optical isomers, or both enantiomers also, in the same bottle. And when you have both of them, remember this is called a racemic mixture. Okay, and again, that's just a 50-50 mixture of enantiomers. The other thing too about this measurement is that if you put an equal amount of enantiomers, then the mixture itself, the racemic mixture right here, is actually now symmetric, okay, on average. So remember, when the molecules are not chiral or asymmetric like this, a symmetric mixture right there will not give you optical rotation. Okay, and that's actually important for us. Okay, so anyway, we want to do some calculations with optical rotation. So again, it's an intrinsic property of a molecule, how much it will rotate. But it's also dependent on concentration. In other words, the more concentrated the sample is, you'll have a bigger optical rotation. Okay, and that's this symbol right here. And it's also it also depends on the what people call the path length. Okay, which is just basically the thickness of the sample. Of course, if you have more sample, either by a higher concentration or by a thicker path length, then you'll actually have a bigger optical rotation. Okay, now we won't go into the details of the concentration and the path length. Besides telling you that a lot of times the concentration will either be neat, which means it's just if it's a liquid, then you just have the sample in the container that you're doing this measurement in. Okay, but if it's actually dissolved in something, a lot of times the concentrations will be in some very strange units, which will be grams per 100 milliliters of solute. Okay, of how much solution you have on here, and then the path length is usually given in decimeters. Okay, and remember, decimeter is 10 centimeters. And the reason is because usually the sample holder is about 10 decimeters long, like that. Okay, this is in case you actually get to do an optical rotation measurement. You'll see that you have these very strange units. Okay, now again, it's all dependent on the particular sample right here. So one sample will have a particular proportionality constant between, or relationship between, concentration, path length, and optical rotation, right? And another compound will have a different one like that. Okay, and so this constant right here, people, instead of using that constant right there, people will use this symbol right here. Okay, and they actually call this a specific rotation. And you might have heard of what do you call it? Well, anyway, so this is called specific rotation because actually it's you've actually maybe heard of specific gravity, and that's just a way of normalizing, to get rid of the units right there. And in this case, specific rotation is sort of already the same thing right here, in that when you report these values right here, you already want to take into account that your sample may be more or less concentrated than somebody else's sample, and that your path length, how thick the sample was is different right here. So basically, what people really report in literature is specific rotation. And again, you can get specific rotation by actually measuring an optical rotation. Put your sample between two polarizers, right? Tilt the second polarizer with respect to the first one and see what angle you get, right? And dividing through by the concentration, the path length, so you don't have to worry about those. And this is really what people operate with. Okay, so this is the property of the compound right there when you've already taken into account concentration and path length. Okay, other things that people will do, for instance, a common thing for people to do is to put a little d up here, and that's to tell you the wavelength, right? And I've been telling you 498 sometimes in videos or in class like this, but it's actually 598, which is the sodium D line. This is the wavelength, okay, in which you're doing the measurement, because it's important to know which wavelength, because you'll observe a different rotation with a different wavelength. Okay, and the other thing that people will indicate also is temperature. So, for instance, a nice cozy room temperature would be 23 degrees, like that. Okay, because also these measurements, right, as will be very dependent on the temperature that the room is in. So anyway, with that information right there, then we would go ahead and, when I ask you questions, or when you get asked questions about optical rotation, more than likely this is the information that you're going to be given. Okay. So anyway, so let's operate now with optical rotation. Okay. So I'm gonna go ahead and first do some thought experiments with you, and then we'll actually define some terms, and then we'll actually give you some problems so you can practice of how optical rotation is used to determine optical purity. Okay, so an important thing to realize is that since enantiomers, right? And let me give you an example of two enantiomers, right? They're that you may actually have consumed recently. Okay, and so let me try to draw this as mirror image so you can actually see that they are enantiomers. Okay, in this case we have one chiral center. Remember, when you have an odd number of chiral centers, the molecule has to be chiral. If you have an even number of chiral centers, that's not always for sure. And if you do have chiral centers but the molecule is not chiral, it's called a mesostructure. Okay, so this compound right here is ibuprofen. Okay, and this stuff is sold as a racemic mixture, right? And so, for instance, you know, I'm not sure which one is a plus or a minus enantiomer, but just for the sake of argument, I'll put a plus and I'll put a minus over here. Now, these compounds are solids like this, so again, when you actually do this measurement, you have to dissolve them in a solvent. So concentration will be important, and again, the sample holder will be one we call it decimeter in length, like that. Okay. So anyway, so here's a thought experiment. Okay, if I put racemic ibuprofen, right, and I dissolve it up in an appropriate solvent to make a solution, right, and because one enantiomer rotates, let's put the polarizer here, and it rotates the plane polarized light in this direction, where this second set of lines represents the orientation of the plane polarized light for the filter most in front of you. Excuse me. And then this other polarizer, this other sample will rotate plane polarized light in the opposite direction right there. Okay, that's counterclockwise. Okay, now if I put the two samples and they're of equal concentration right there, what I'm hoping you will see like this is that the rotation in this direction clockwise and the rotation in this direction counterclockwise will cancel each other, so that when you observe the racemic mixture like this, it will appear that you just have a symmetric compound in there and that there is no rotation that's going to occur. And remember, that occurs because, yes, the racemic mixture overall is a symmetric compound like that, or a symmetric mixture. Okay, so we use this property actually to tell us how pure a sample is when you have two enantiomers and you just have those two enantiomers in there like that. And this is important because basically, remember, when organic chemists make things, and this is why ibuprofen is sold as a racemic mixture, okay, if they start off with an asymmetric compound like this, then that's all you're going to make. Like, you're going to make a racemic mixture. You have to make, whereas when you make something symmetric like this, then you end up with something symmetric. Okay, and so because of that, then when you go through the process of purifying these things right there, then you're basically going to try to determine how much of one enantiomer you have versus the other. Remember why this is difficult, right? Because enantiomers have the same physical properties like this. And because they have the same physical properties, it's difficult to separate them, right? And so therefore, for instance, let's say you had done a TLC, okay, thin layer chromatography. Well, the silica, the silica is a symmetric material overall on average. I'm not saying that there isn't an asymmetric structure, at the atomic level or the molecular level of the silica plate, but on average it's symmetric. So, when you elute, the plus enantiomer versus the minus enantiomer, they're going to travel the same amount. So that over here, if you had a racemic mixture and you try to separate them using silica on a TLC plate, you will not be able to do that. You will not be able to separate these compounds either using distillation, using recrystallization like this, because again, they have all the same physical properties, the same solubility and everything like that. Okay, so once you figure out how to separate these compounds right there, then you better make sure that you know how pure they are like that. And so, for instance, here's a method that one of my students has used for this, and And the method is basically that, well, since this is important for biological systems right here, okay, if I go ahead and put the racemic mixture, okay, and okay, here's my racemic mixture. Okay, here I put the plane of the ibuprofen in a different direction, but you can tell that they're different because let's see, let's do this 1, 2, 3. So this is the R enantiomer, and then this is the S enantiomer, right? And then what he's done is then he's used an alcohol, okay, where you have different size alcohols in here, and then use a biological reagent. Okay, in this case he used something called Candida rugosa, which is from a fungus, and it's an enzyme called a lipase. And this lipase is usually meant to actually hydrolyze fats and oils like that. Okay, but because this lipase, right, from this enzyme right here is an asymmetric thing, it's made up of a protein that has all asymmetric components like this, then what this compound or what this enzyme catalyzes is basically the reaction. It should look like a Fischer esterification, but no, there's no strong acids required. But anyway, it catalyzes the esterification, okay, of one ibuprofen enantiomer, and it leaves the other one behind. Okay. Now it's not a perfect reaction, and this is why you have to use some method. We actually use chiral chromatography. This is a column that actually has cellulose embedded in it. So when these compounds travel down this column, they actually are in an asymmetric environment, and they actually elute at a different time. Okay, this would be like actually putting a chiral compound on your TLC, and then actually being able to separate enantiomers because each enantiomer is traveling at a different rate because their interaction with the chiral silica or the material that's on the TLC that is chiral like this is non-mirror image. Okay, so anyway, so one way is to actually separate and determine how much of this you have and how much of this you have left over like this. Okay, but another way is actually to use optical rotation. In other words, after you went through all this trouble of trying to purify a compound so that you only have one enantiomer left behind like this, then you want to actually determine this by actually doing this measurement, which is basically putting your sample inside a polarimeter. Okay, so let's work on some examples here. Okay, so let's say I have a molecule R and I have molecule S. Okay, now I'm just assuming that it has one chiral center, and that's why I'm using the R and S notation. Okay, you could have more than one chiral center and also have a chiral molecule, but let's just for simplicity's sake let's use this. Okay, now remember you cannot actually guarantee whether the R is plus and the S is minus. Okay, in fact it could be the other way around. Okay, okay, so don't use that as a criteria. Okay, the only criteria you can use, right, is that if R and S are enantiomers, then R and S must have what? Opposite optical rotations. So if I do associate R with minus, then I do know that S has to be associated with plus. Okay, so that is a given. But of course there could be another compound where R is associated with plus, and then you would have to respond, okay, then S must be the minus enantiomer. Okay. Okay. So anyway, so let's start off with compounds like this, R and S. Okay. And for argument we'll say, okay, the R compound, the R enantiomer has a plus rotation and the S has a minus rotation. Now again, remember, enantiomers are difficult to separate, but diastereomers, constitutional isomers, non-isomers, all of those are simple or much simpler to separate because they should all have different physical properties like that, even if they're slightly small. But enantiomers should have the same physical properties. Okay, so now you have a sample. Okay, so here's your beaker Wheater sample, and you purified everything, but you still have some plus and you have some minus. And so you want to do this optical rotation measurement like this, right? Plane polarized light, rotation in some direction, plus or minus like this. And then that will tell you, first thing it'll tell you is which one you have in excess of these enantiomers. So for instance, if you go ahead and and do your measurement, right, and the rotation comes out to be plus, then it must be that you must have more plus enantiomer. Okay, if it comes out to be a minus rotation, then you know that it must have the more of the minus enantiomer in there, like this. Okay, and again, it's because what, plus rotates in one direction, and then what, minus rotates in the opposite, right? If they're equal, then overall, right, then you would get a zero result right there. In other words, if I rotate clockwise in this direction and I rotate counterclockwise in the opposite direction, overall the result would be this if I have an equal mixture of compounds. Okay, but if the plane of polarization starts there, right, and I have more plus enantiomer and I have a little bit of minus enantiomer, then the result of this whole thing will actually that you will see an overall what? You will see an overall plus rotation, right? Okay, and it would be like, actually, let me go back here. It would be like the plus being canceled by the minus, right? Proportional to the amounts that you have of each one of those right there, okay? Okay, and so this measurement of optical rotation can be used to actually measure how much you have of each enantiomer. Okay, so let's give you some examples here, okay? Let's start off with a compound that has a pair of enantiomers that have optical rotation of plus or minus 100 degrees, okay? Just as a number to start off with, like this, okay? And again, we were arguing before, okay, for our example, S will be plus and, R will be plus and S will be minus right there, okay? Okay, now the question is, well, what if I have a mixture of these two enantiomers, and what I actually observe is a rotation of 90 degrees when I've made sure that I've removed all other impurities right there. And let's say just from front like this, that the actual rotation is minus 90 degrees. Again, remember, which one do you have in excess? Do you have the plus or the minus enantiomer in excess if you have a 90-degree rotation? Of course, the answer is you must have what? The minus enantiomer. You must have more of the S if you want to associate it with the S in this case right there. Okay, now can we tell anything else more from this? Well, the other thing we should realize like this is that this resultant minus degree, right, is telling us that we do not have a pure sample in terms of enantiomers. We have a mixture of enantiomers. It may be enriched. That's a fancy term, you know, for telling you that you have more of one than the other. It may be enriched in the minus enantiomer, but it's still not pure. Okay, and so what people come up with then is they come up with this concept, and it's called enantiomeric excess. Okay, and let me give you the enantiomeric excess definition. Okay, let me give you two definitions of this. Okay, because it's just a slight mathematical differentiation right here. Okay, so enantiomeric excess means, okay, I'm going to take the concentration of the plus. Okay, well in this case I have more of the minus, so I'm going to go ahead and say, okay, if you take the concentration of the minus, right, and you go ahead and, okay, and you add, okay, or excuse me, you subtract, okay, now this is a little funny, okay, if you subtract the concentration of the plus, because in this case you have more of the minus than the plus right there, right, okay, that's why you're getting the 90 degrees, right, okay, because if you had pure minus, you should have gotten 100 degrees, right, but because you have some plus in there, okay, then you must be what? You must be canceling the rotation of the minus with some other plus on there, okay? Now the excess definition then goes ahead and says, well, okay, how can we actually sort of normalize this data or normalize this information? And the way we do that is we go ahead and divide through by the overall concentration, right? And this is basically saying, okay, this is what you're observing, right, relative to assuming that the whole sample was just one thing, right? And therefore, this is what you're seeing in enantiomeric excess right there. Okay, now, why is this important, or why is this definition important? Because we can actually get the enantiomeric excess very easily like this by these two measurements, okay? This minus 90 degrees, okay, is proportional to the fact that what? We have more of one enantiomer than the other, right? But it's not pure, okay? And this 100 degrees up here, right here, okay, is assuming that it was pure, okay? So So let me put minus 100 degrees here in the denominator like this, right? Okay, so this enantiomeric excess right here, okay, which in this case would turn out to be 0.9, or if you want to write it down as 90% right there, okay, is an indication of how pure the sample is, right? Now keep in mind, okay, this enantiomeric excess, right, or optical purity if you want it right now, okay, this 90% right here, right, is not really telling you that you have 90% of one enantiomer, okay, and 10% of the other right there. To get this 90 number right here, what you really had, and let me show it to you in this way, you really had, okay, 95 or a concentration of the sample that was rotating the, and these are all specific rotations, okay, that was rotating the sample minus 95 degrees, and then your other percentage of your sample was rotating the sample, okay, 5 degrees, right, in the opposite direction. And this is where you got the 90-degree rotation in the minus direction. And here in the bottom right here, okay, okay, of this whole thing right here, right, this is where this came from. And here in the bottom right here is if the sample had been pure right there, okay? So when I say an enantiomeric excess of 90 degrees right there, I'm not really talking about concentration of one sample or another. I'm really talking about the difference in the concentration of one enantiomer versus the other, okay? Okay, so that's an important thing on here. So anyway, we've defined enantiomeric excess. So enantiomeric excess, and here's shortcut EE, okay, is how much you have of one enantiomer. In this case, I guess we're using the example, right, minus how much you have of the other enantiomer, right, versus the total concentration of both enantiomers right here. And remember, this enantiomeric excess can be gotten by taking the observed, okay, I'm going to go ahead and put observed, right, specific rotation of the observed sample versus the specific rotation of the pure sample. Okay, in other words, what you're expecting to see if you just had one enantiomer. Okay, now that you have this information right there, okay, then you can actually easily get enantiomeric excesses. So for instance, if somebody says, oh, okay, I have a mixture of, let's say I have a mixture of okay, let me go ahead and get this. Okay, let me say I have a mixture that rotates plane polarized light 75 degrees, right? And what I want to determine then is how much of each one of these I have. Okay, and you know, I'm going to assume that that the pure enantiomer in this case is like the same example, either plus or minus 100 degrees right here. Okay. Okay. Then the first thing I'm going to do is calculate enantiomeric excess, and so in this case it would be what, 0.75 or 75% right there, enantiomeric excess. Okay, once I have this down here like this, now let me show you how you can use this information to determine how pure the sample is, and then we'll back calculate to go ahead and show you that that this is actually true. Okay, so for this treatment right here, I'm going to go ahead and assume that you know, the overall concentration, some of the concentrations here is just 1, okay, or if you want 100%. Okay, I don't want to deal with, you know, that that you have with a different I don't want to deal with the units actually of the concentration. Okay, so I'm just going to make this all a relative concentration, okay, where the sum is equal to 1. Okay, okay, now that means, okay, and here I'm moving my pen here, so it did strange things, but this means basically then that I can rewrite my enantiomeric excess right here as being equal to let's see, plus minus, okay, as being equal to that, right? Okay, let's see. Now, what I'm going to do then is I'm going to go ahead and write, okay, whoops, that shouldn't have been plus, that should have been minus here. Okay, oh, and I changed my, from what I'm doing in my problem here. Okay, so let me put minus here and let me put plus here. Okay. Okay, So now I have my enantiomeric excess, because I decided that the overall concentration is going to be 1, is just equal to the difference between the concentration of the two enantiomers. And then I decided, again, I just set the total concentration to be equal 1. Okay, once I have this information, now all I have to do is add up these two numbers. On the left side are these two equations. I'm going to add those together. And then here on the right side, okay, I add those two together like this. And what happened here? I canceled out the minor enantiomer from this measurement. And then when I go ahead and divide through by 2, then I actually get that the concentration of the major enantiomer, which in the problem that I was giving you, right, was the minus enantiomer right there. Then you get, well, its concentration must be the enantiomeric excess plus 1 over 2. Okay? And that's why I wanted you to learn what enantiomeric excess is. Okay, so now let's apply this. So don't forget this formula right here, okay? The enantiomeric excess of the major, don't worry whether it's plus or minus, but the enantiomeric, the concentration, right? The concentration of the major enantiomer is given by the enantiomeric excess plus 1 divided by 2. Okay, so let's go back here to a problem that I was giving you. Okay, now in this problem, it's actually different. Okay, I'm telling you the plus enantiomer is the one that's the major, right? Because I got a measurement of plus 75 degrees. Okay, so now let's apply. How much do I have of the major enantiomer if the optical rotation is 75 degrees? Okay, and so what I do is I say, okay, the concentration of the, let me not use plus or minus, let's use major, okay, is equal to the enantiomeric excess plus 1 over 2. Okay, now I want to get the enantiomeric excess, right? And remember, enantiomeric excess is the difference over the sum, right? Okay, but it's also what you observe, right, over what you expected. Okay, and then we add 1, and then we divide through by 2. So this turns out to be 1.75 divided by 2, right? And if I do my math correctly, right, let's see, this is almost 9, but it's not, so it's 0.8, and then let's see, that would give you 1.6, and divide through by 2. So that would actually give you 15. So 15 divided by 2, 7.5. Or if you want, 87%. Okay. So this is telling me that the major enantiomer in a solution that has an overall rotation of plus 75 degrees right there is actually 87% of one enantiomer and 12.5% of the other. Okay, these are percentages right here, right? Okay, and let's go to a new slide just to confirm this. Okay. Okay, so to confirm this, right? A sample that has an optical rotation of 75 degrees, when the pure enantiomer has a rotation of either plus or minus, right? Okay, we said is composed of 87.5 of the plus enantiomer and, okay, oops, what am I using? Okay, 87.5% of the plus enantiomer and 12.5% of the minus enantiomer, right? Okay, now let's see if this is true, okay? And the way we get this is, well, let's go ahead and put it back into the enantiomeric, let's go ahead and put this back into the enantiomeric excess formula. Okay, and so the concentration of the major enantiomer is 87.5, and then we subtract the concentration of the minor enantiomer, right? Now remember, the bottom we decided to set to 1, right? Because this is a relative concentration on here. So if you take 87.5 of one and you subtract 12.5 of the other right there, okay, then you actually get, well, which is the result, which is 75%. Okay, of that. Now, what if you wanted to, so the result comes out to be this, what you expected on it. Okay, now let me give you another example here, because I just happened to use 100% like this, but maybe that wasn't the best example on here. So let's say we have a mixture of enantiomers where the pure enantiomers would have a rotation of, let's say, 59 degrees. Okay, and you're given a sample, right, that has has an optical rotation of minus 13 degrees, right? And so what you want to do is you want to go ahead and determine, okay, how much do you have of each enantiomer right there. Okay, and so the fast way of doing that is saying, okay, the concentration of the major one, right, is equal to, okay, the enantiomeric excess, which would be, okay, 13 over 59, okay, and use the same sign for both of them like this, okay, otherwise you'll get confused, plus 1 divided by 2, okay, so in this case then you would get 1 and 13/59 over 2. Okay, I'm going to pull out the calculator here, okay, and do the math here. Let's see if I can go to accessories here quickly and show you with a calculator how to get these results right here. Okay, so we're going to get what? 13 divided by 59, okay, plus 1. Okay, that's the numerator. And now we're going to divide through by 2. Okay, that's the denominator. And what we get from this is, okay, the calculator said that this was the overall concentration of the major enantiomer is 61% Okay, 61%. Okay, now let's go ahead and do the back calculation to see if this is true. Okay, and so if we do the back calculation, okay, then then we would go ahead and say, okay, you have 61% of the major enantiomer, right? And then you have what? What's the complement of this number? That's what? 39%, right? Of the other enantiomer, right? And basically, right, if you take the difference over the sum right there of this, right, then you actually get a number. Let's see, we should be able to do this, right? We don't need a calculator for this. So if you take the difference here, it should actually be a difference of what? 22, right? 22%, right? Okay, a 22% difference. Okay, let's go ahead and add these numbers just to make sure. 2 plus 9 is 11, and 2 plus 3 is 5, plus the 1 is equal to 6. Okay. So anyway, so the enantiomeric excess in this case would be 22% like this. Okay, but we still haven't gotten back to the 13%, just to make sure that this is true right there. Well, the way you get to this is, all you have to do is check, okay, is, right, 13 minus 13 over minus 59 degrees, okay, is that equal to, okay, 22%, right? Or work it around, 0.22, right, times 59 degrees should give you 13 degrees, okay? So let's do that on the calculator just to prove it. Okay, so we'll take 0.22, oops, let's clear that. Here's the decimal, 0.22, or 22%. 22% of what? 59 degrees, right, should be equal to 13 degrees right there, okay? Okay, so we were able to get that, okay? So these are the kinds of calculations that you should be able to do. Okay. Now the other fun one to do is actually not only how to get the enantiomeric excess and how to actually get the concentrations of that, but actually the most one of the more useful calculations is, okay, if you're given a sample of a certain enantiomeric with a certain enantiomeric excess like this, okay, and you're given this rotation like this, can you actually get, okay, the what do you call it, the rotation of the pure enantiomer, okay? And this is actually done a lot like this because it is difficult to separate enantiomers, and so you want to actually come up with a goal in terms of what would actually constitute a pure sample like that. Okay, so let me give you an example of a problem like that. In this case, for instance, let's say I give you that by another method, okay, you determine that that the sample, right, was, for instance, was actually 32%, okay, 32% of the minus enantiomer, okay, and then you're told that this mixture, right, and it's only a mixture of the two enantiomers right there, then you're told that this mixture has a rotation of 50 degrees. Okay, and you know it's not pure, right? Okay, it's not pure right there. So what you want to determine, right, for this problem right there, is basically what would be the rotation of a pure sample right there. Okay, and you just can't do it, like you might have been used to, right? If you're saying, oh, it's 32%, right? So shouldn't I just take 50 degrees and divide through by 32%, and actually this would be the rotation of the pure enantiomer like this? And the answer is no, that's not how it works right there. Because remember, what you're actually observing here is the difference between the rotation of one enantiomer and the other like that. Okay, so what you have to do then is, okay, well, what you're really observing here is what? 32% of the minus enantiomer, 68% of the plus enantiomer, because they have to add up to 100%, right? And you go ahead and calculate EE, right? And you come over here and you say, okay, that's 68 minus 32%, right? Okay, and you're being told, okay, 50 degrees, right, is what you're observing right there. That's what goes in the numerator. Okay, and so this is really what you're trying to determine. What would be the optical rotation of the pure sample? So when you take the difference of the two, right, then in this case it comes out to be the number 36, right, or 0.36 right here. And then you can do the math now, right? Okay, and the math now tells you that what you're looking for is actually 50 degrees divided by 0.36, right? And so we can do that, right? And we say, okay, so 50 divided not by, okay, let's back up here. 50 divided not by 0.32, but actually by 0.36. Okay, 36%. Okay, and what you get in this case is that the optical rotation of a pure sample would be pretty close to 139 degrees. Or you can write, which is all the decimals that you need for this right here. Okay, and it's all because one is canceling out the other like that. Okay, and it would not have been the 0.32, which would have given you somewhere close to 250 degrees like that. Okay, so hopefully you'll understand some of these optical rotation questions like this, and be prepared to answer questions that you're given in class.